Fei Xie from the great city of Edinburgh, and she'll tell us about her new work about Nodal, quintic, del Pezzo threefolds.
Okay. Thank you very much for the invitation and introduction. So I will talk about today the specific type of singular threefolds and then discuss their derived categories. So first, I will set up the model to study the singular threefolds and then talk about the main result for the derived category. And also there's a related work, and I will discuss the relation between these two different methods. And also, and then the second plan for the talk is, since the model I will use to study the threefold is a quadric fibration, so we recall what is the Clifford algebras and the spinor sheaves of quadrics, especially singular quadrics. And then lastly, I will talk about the proof for the main result. For this talk, the base field will always be algebraic closed and then characteristic 0. And then, so first, maybe let me mention the precise definition for this del Pezzo threefold I will study. So here, I'm allowing some mild singularities. So the definition is a quintic del Pezzo threefold is a normal integral projective threefold X with at worst terminal Gorenstein singularities, such that the anti-canonical divisor is ample divisible by 2, and the degree is 5. And then, so there's a classification for such a threefold. And then it tells us that.
I can ask, so terminal Gorenstein implies isolated, right?
Yes, that's correct. So it tells us, oh, sorry, it doesn't happen much. X is smooth or has M nodes, where M is 1, 2, and 3. And then since I will mostly talking about the singular threefolds, so we just give this a notation and then use XM to indicate this is a threefold with M nodes. And then, moreover, X is unique in each case. And then lastly, for each of them, they're codimension 3 linear sections of Grassmannian 2-5. And so, so actually, the singularities of this linear section is somewhat controlled by the dual linear section. So just to describe this relation, and I will write this linear section out more carefully. So I will write this as this way. So V and W are vector spaces of dimension 5 and 7. So when I write it out this way, I can define the orthogonal vector space, which is defined as the kernel of the natural map of this surjection coming from taking the due of the injection. And then we have the dual linear section, X sharp. Which is the intersection of this W perp with the Grassmannian of the dual space. So then we know, so actually here, this is a 3-dimensional space. This is a 3-dimensional family of hyperplanes you use to intersecting to get X. So then we have X is smooth if and only if X sharp is empty. And then if X is the threefold with M nodes, then X sharp will be a disjoint union of M points. And then if you choose this W7 generic enough, then the converse is also true. Then here, we'll focus on talking about the singular cases. So we'll always have X sharp is not empty. Then we can pick a hyperplane such that it corresponds to a point in X sharp. And then we'll know that these XM will always be contained in a hyperplane section. And then this hyperplane section has a singular locus, denote this by SH, isomorphic to P2. And then from here, we can actually get the node corresponding to this point H, where if you intersect the singular locus with the threefold, then this is the same thing as intersecting P2 with the other two hyperplanes you will use to get X. Then you will get this is actually a point, and this is a nodal point. On XM. So if you're in the 2 nodal and 3 nodal cases, then you will have a second or third point in X sharp, and then you use the hyperplanes corresponding to those points, and then similarly you can get the second and third node this way. So here we have this Trelson node, which exists in all singular cases. Then we can construct a rational map this way. So, so I will represent this by a 2-dimensional subspace of a V5. Then there's a natural map to the Grassmannian of the quotient, sending a 2-dimensional subspace to the image in the quotient. And then, so, sorry. Ooh. So for this smaller Grassmannian, if you do the Zhuokai embedding, then you just get an isomorphism. So actually this rational map is a linear projection. And I will mention, well, you will see in a few minutes later why I would mention that this is a linear projection. So this is P2. And now, so since XM is always contained in the hyperplane section, we'll restrict the rational map to the hyperplane section. Then we'll have the following picture. So the image is also intersecting with this. And then here, this will be P1. And then we can resolve this rational map and then get on the top, this is a Grassmannian 2-4 bundle over P1. Ooh. So let's call this F, this P. And then on this side, if this is a point, then the fiber is just the Grassmannian to V4. So you can see this is a smooth 4-dimensional quadric contained in this hyperplane section. And then this will always have the point, which is the given node. And then on the other side, this map F, this will be a birational morphism. So the exceptional locus is, sorry, P2 times P1, which is the Grassmannian 203. And then it contracts to the singular locus of the hyperplane section. And now, so if we restrict the whole picture to the threefold, then this is what you will have. So on the one side, as I mentioned, this is a birational morphism. Since the intersection of the singular locus with XM is just this node, so this is actually a small contraction of P1 to the point. And on the other side, this is a quadric surface fibration. So you can also describe YM as contained in some P3 bundle, where this E is this rank 4 vector bundle, and then Y is a zero locus of some quadratic form. And then on the other side, so as I mentioned before, the exceptional locus of Fm, on the other side, this is just a projectization of this sublime bundle. And then this is a smooth section of the quadric fibration. So here, well, this birational map, this is a small contraction, and it only changes the variety near the chosen node. So it only resolves the singularity at this one node. It doesn't change the points outside of the node. So this total space, it will still have nodal singularity if M is 2 out of 3, but the number of nodes will be decreased by 1. And then, so here, since now we have described the threefold as the small contraction of a quadric fibration, and then for both of them, we know how to study their derived categories. So going this way, then we can find out a semi-orthogonal decomposition for dBxm. So using a different method, the same result is also obtained by Pavic and Shinder. So let me mention what is the main result. So here we can have this semi-orthogonal decomposition where you have 4 components. So this Rm and R2 are finite dimensional algebras I will mention in a second. And then the other 2 are trivial ones, which is O and O1. So as I mentioned, this is finite dimensional algebra. So actually, when M is 1, this is just the base field K. And then when M is greater than 1, then this is the path algebra, given by M minus 1 vertices. So A1, B1, AM minus 1, BM minus 1 with this relation.
I guess as it is written, it doesn't make sense, right? AI BI equals probably BI plus 1, AI plus 1, or something of that sort. I mean, the left hand side and the right hand side of the equation.
Oh, sorry. I meant equals to 0. I forgot to mention. Yeah. So those first, so both of them equals to 0. Maybe it's better to write it that way. Thank you. Yeah, that's what I meant.
So if m equals 1, right, then how many summons do you get?
Oh, 1 and just the k.
So you get k and the singular. Oh, okay, yeah, thanks.
Yeah, I guess maybe it's better to write this way. And then, so for both Pavic and Shinder and my methods, our ideas are the same, where we would try to find a rational map from XM so that you can factor that rational map into morphisms. You know how to describe the derived category, and that's how you get dBXM. And then the difference between our approaches is we use the different rational maps. So maybe let me briefly mention what they did and then what's the relation with my method. So for Shinder, what they did is they picked a P1 in the smooth locus of X. So of course, you can also do this for smooth threefold as well as the singular ones. And then you can do the linear projection from the line to P4. And now the image of this will be a three-dimensional quadric, which could be smooth or nodal. And then if factor as on the one side, this is just the blow up of the line. And then on the other side, this is the blow up of the nodal curve of genus 0. And then, so what I did, the rational map I used is kind of exactly the opposite. So as I said, if you recall, I mentioned before when I constructed the rational map for the Grassmann 2.5, that was a linear projection. So after you restrict, it's still linear projection, and it's a projection from P4 to P1. And the base locus is the intersection of P4 with XM. And now this is a vertex, the cone over the same nodal curve C with vertex, the point I chose. So since I have to choose a nodal point, it only works for a singular threefold. So this concludes the first part. Are there any questions?
Can you say again which curve is this? So C is what? C is
the nodal curve of genus 0.
Which sits in the quintic del Pezzo threefold, or it's
yes. It sits inside it.
I guess this is just the intersection with the embedded tangent space to the singular point, right? So P4 is the embedded tangent space in this case, right?
Yeah, I think you're right. I didn't think about this way. So for me, the space locus is a union of all the lines passing through the node. I guess yes. then it's the embedded tangent space. That's right. Okay, so if there are no more questions, I will move on to the next part, where I will talk about the Clifford algebras and the spinor sheaves. So we choose a quadratic form of a vector space V, and then consider the corresponding quadric. Then the Clifford algebra, by definition, is given by the tensor algebra of the vector space V, quotient out by the relation generated by V squared equals to QV. And then, so you can easily see that if the quadratic form is 0, then the Clifford algebra would just be the exterior algebra. In general, so this BQ may not be isomorphic to the exterior algebra as algebras, but they're still isomorphic as vector spaces. And then by the definition, it's easy to see you can have a Z-2 grading where the even part you consider all the even tensors. And then this is an algebra. And then the odd part, you consider odd tensors. It's not an algebra, but this is a module over the even part. And then, so classically, for any smooth quadrics, you have spinor bundles, which are locally free sheaves. But actually, for singular ones, you can kind of generalize that definition. So actually, for any isotropic subspaces of the quadratic form, you can have a spinor sheaf. So let W to be the isotropic subspace, which means that when you restrict the quadratic form to the space, this is 0, and this is the same as this linear space is contained in the quadric. And then, so of course, you can see the exterior algebra of W is a subalgebra, and then you can consider the principal right ideal generated by this one-dimensional subspace, which if you choose the basis of W, then the ideal I is just the ideal generated by the product of this basis. And then similarly as before, you can have the even part and the odd part. So I denote the even part by I0 and the odd part by I1. So actually the odd part can be described in terms of the even part by using this tensor. So it's kind of enough to know the even part. And then from here, we can consider a map from O-1 over the projective space, tensor the ideal to O tensor the ideal, where over the point V, this map, which is a map from the ideal to the ideal, is given by the right multiplication of this vector V. So from this description, you can easily see that when you compose delta with itself, you just get its multiplication of V squared. And then in Clifford algebra, this you have this relation where V squared is equal to Q. So then you will get the decomposition is Q. So this delta is actually a matrix factorization of the quadratic form. And then from here, then we can complete this map and then to get the spinor sheaf. So we will restrict to O-1 tensor the even part of the ideal. So we have the O-1 tensor I0 maps to O times I1. And this will be injective, and then define the co-kernel to be SW, which is a spinor sheaf associated with this linear subspace in the quadric. So here,
I'm sorry, this is a sheaf on what? On
this is a sheaf on, yes, that's a very good point. This is a sheaf on Q. So I should probably maybe make this precise. This is a supported on the quadric. This is a sheaf on the quadric. And then as a sheaf on the quadric, it's always reflexive, but not necessarily locally free. So actually, this is locally free if and only if the linear subspace you choose is contained in the smooth locus of the quadric. There are also many more properties of this SW which are determined by the isotropic subspace, but I will not go into details about that. And then since the model I will be using, I will have a quadric surface fibration.
I'm sorry, does it matter if W intersects the kernel of Q or not?
So when the W intersect with the kernel, that's the locus where the rank of the sheaf will jump. That's where, yeah, this sheaf will not be locally free.
So if it does not intersect, then the sheaf is locally free, right?
Yes, exactly.
And if W is exactly the kernel of Q, then what is this sheaf? Okay, then I understand. Then this is essentially pullback from the quotient of, I mean, then Q is a cone, and this is basically the pullback from the base of the cone, and then reflexive extension. Okay, thanks.
Yes, exactly. That's right. This construction and the properties are studied by a work of Addington. And then since I will talk about quadric surfaces, so let me just focus on the surface case and then consider the dimension is 4. Then, so we'll have a quadric in P3 and then consider the quadric co-rank at most 2. So for each quadratic form, it will correspond to a symmetric bilinear form. So the rank of the quadratic form is just the rank of the matrix. And then, so then we will also pick any smooth point on the quadric and then denote Sx be the spinor sheaf associated with the point. Then we'll have, well, since now X is a smooth point, it's away from the singular locus, so the sheaf is actually locally free, and this is rank 2. And then the dual sheaf will be isomorphic to the sheaf tensor with O-1. And then lastly, you can find a regular section of this vector bundle such that the zero locus is the point you start with. So you can actually describe this section very explicitly. So for a point on the quadric, it can be represented just by an isotropic vector, and consider this as your isotropic subspace. Then you can make this map delta and then do the co-kernel to get the sheaf. Then we'll have, by definition, this map from the odd part of the ideal to the sheaf. And then in the odd part, then you will have this vector generated by just this vector. And then this will give you a section of the sheaf. And this is that section that is regular with zero locus X. So combining 2 and 3, we will have a kazoo resolution for the skyscraper sheaf of the point. This should be S2, but this is isomorphic to just tensor with O-1, so I would just write it this way. And then because this construction, you can see is very canonical, so you can also generalize this to fibrations, and that is the part I will use later. So more concretely, let's discuss what happens in different rank of the quadratic form. So when the quadric is smooth, then the surface is just a P1 times P1. In this case, the spinor sheaf is just O10 direct sum O01. So classically, over this smooth quadric, the spinor bundles are exactly these two line bundles. So here, your extension, the generalization of the definitions telling you that you're also considering the extensions of them. So in this case, it's a direct sum. And then when the corank of the quadric is 1, then you will have, this is a cone over a smooth conic. If you remove the vertex, then there's a projection from this space to P1. Then consider the pullback of O1 to this open subset, and then do the underived push forward to the cone. Then you have a rank 1 reflexive sheaf, which is also spinor sheaf, but related to a line, not to a point. In this case, your locally free spinor sheaf Sx is just the unique non-trivial extension. And then lastly, when you have the quadric's corank 2, then your quadric will be the union of two P2 intersecting at a P1. So a smooth point would be a point away from the line. So assuming the point is the first P2, then the sheaf Sx, when you restrict to the P2 containing the point, you get, this is the tangent bundle of P2 tensor with O-1. And then if you restrict to the P2 not containing the point, you will have, this is O plus O01.
So you can actually, in each of these cases, we have a quadric, singular quadric with the two exceptional objects, and you're describing the orthogonal to those two exceptional objects, right? I mean, on a quadric, we have like O and O of H, and for example, O10 plus O01 is the orthogonal, so that like in each case, it's a spinor part of the quadric, right? Kind of.
But yes, exactly. That's correct. Any other questions for this part? Okay, so now we can move on to talk about the proof of the main result. So just quickly recall, like we have described this rational map and then the factorization, where XM is the quintic del Pezzo threefold with M nodes, where you have a rational map can factor as a birational map, which is contracting P1 to a point, and then this space Y is a quadric surface fibration, given this way, where on one side, E is exception locus, on the other side, is a smooth section. And then to describe the dBxm, we'll first describe the derived category of the space Y. And since this is a quadric fibration, then by the result of Kuznetsov, we have the following decomposition, where you will have 4 components, where the first component is non-trivial. Oh, sorry, 3 component. I was wrong. And then you also have the pullback of dBp1, and the pullback of dBp1 tends to 01. So here, this BM0 is just the even Clifford algebra of the quadric fibration. And then this derived category would be the derived category of right modules over this algebra. And then when you forget the algebra structure, they're just the coherent sheaves of P1. So basically you can see these 2 components are the trivial ones, and then the main work goes into understanding this non-trivial part. So first of all, we'll describe this embedding explicitly, where this is given by a Fourier-Mukai functor. And then the kernel K, I call it Km, is a rank 4 vector bundle on the total space of the quadric fibration. And then it's defined in a similar way as the spinor sheaves, where you also have this map delta, which is a right multiplication. But here you would consider the whole even Clifford algebra, and then the whole odd Clifford algebra. And then it will be going from O minus 2 to O minus 1. And then K is the whole kernel of this map. And this is supported on the quadric fibration Y. So I should.
And why is it a vector bundle?
Oh, so basically you can think of this K as the spinor sheaf corresponding to the empty isotropic subbundle.
But then, as you explained, it is just a reflexive sheaf, no?
But because you're choosing the empty, like the empty linear subspace of the quadric fibration, of course, is away from the singular locus, so it's always locally free.
I'm a bit suspicious about that, because the total space of your quadric fibration is singular when m is greater than 1, right?
Yes, that's right.
So I have an impression that Km is not locally free at the singular points.
Well, it's actually described in your work that it's always locally free. You can do a local computation to find out like this is always locally free.
Mm-hmm.
But I guess the explanation I gave you before is it's just easier to explain that way. Like you're choosing empty subspace, it works. So you still get locally free sheaves.
Okay.
Okay. Okay. So to understand this non-trivial component, we'll make use of the Hilbert scheme of lines in the fibers of the fibration. We'll denote this by HPM. So by the definition, then there is a natural map to the base P1. And we'll consider the Stein factorization of this map, where it factors through a morphism with the connected fibers and an affine map. And this affine map is actually a double cover of P1 ramified along the locus where the determinant of the quadratic form is 0. And then so this is exactly the locus where your quadric will be singular. And then, okay, so maybe before I go into details, just quickly say, so we have to work with 3 cases where m is 1, 2, or 3. So when m is 1 and 2, the quadric fibrations, the fibers will be either smooth or corank 1. And in that case, it's a classical story to use the Hilbert scheme of lines to understand this non-trivial component. But when m is 3, then you have a fiber that corank is 2. Then you have to do a bit more work to try to understand this category. So instead of using the whole Hilbert scheme of lines, I will actually just try to consider a subscheme where I consider the lines and the fibers where they intersect the smooth section. So this will be a subscheme. And then there will be a map from the subscheme to the double cover, then to P1. So first, okay. You can describe the subscheme, and then this is when m is 1, this is just the P1. And then when m is 2 and 3, you have a chains of MP1s.
So can I ask about the double cover? So when you have union of 2 planes, so corank 2, yes. It's new components, right? It's like it's reducible, the thing. I mean, if you look at lines in a union of 2 planes.
But like, okay. But like whenever you have a, let's be safe, say a quadric surface fibration with smooth generic fibers, you do Stein factorization, you always get this double cover.
But isn't CM reducible? Like with vertical components over the most singular fibers?
I think it will still be a scheme over the do numbers over that singular fibers. Okay. So let's see. So here's the thing. So you can always find a rank 2 vector bundle Vm on this curve, such that if you apply this push forward functor from dB of the curve equipped with the sheaf of endomorphism of the vector bundle to this non-trivial component, and you will have, this is an equivalence. And then by Morita equivalence, this is equivalent to just the dB of the curve where the map can be explicitly given by tensor with the dual of the locally free sheaf. The reason here that this is V dual is because instead of V, is because V dual would be the vector bundle that has a natural right module structure over the endomorphism. And then, so lastly, if you combine this equivalence from the second step, second part, together with the fully faithful embedding, then you will have a fully faithful embedding where when you pick the structure sheaf of the curve, in the first map, you will map to I0, where I0 is the ideal of the even Clifford algebra. associated with the isotropic subline bundle O inside of the rank 4 bundle E, where this isotropic subline bundle is the line bundle corresponding to a section. And then once you have this, then it's easy to see that the image of this ideal under this fully faithful embedding would be the spinor sheaf associated with a smooth section. Because by definition, this is just a co-kernel of the map delta when you're considering here it's I0 and here's I1. And then by definition, then it's this is the case. So so one important thing that I will use from this fact is that then this spinor sheaf will have a regular section such that the zero locus will be your section E. So you will again have this kazoo resolution given in this way. So since I don't have the time to maybe go over all the details, maybe let me first tell you why this proposition will be enough to deduce DBXM to prove the main result. So let's see. So first of all, there's a work by Urban telling you that the derived category of this chain of P1s will have a decomposition where it has two components. And then one is equivalent to dBRM. The RM showed up in the main result. And then the other part is the structure sheet. And then the second thing is that the push forward of F, this birational morphism, will gives you a map from dby to dbx. And this is essentially surjective. And then the kernel of this functor is exactly the subcategory generated by OE twist -1. And then now, since we would have this kazoo resolution, so it tells you exactly how you can find out where does the kernel sit inside of dBym. And then from there, you would know how to descend, how to like do the mutation, and then the new collection can descend to the decomposition of dBxm. So then maybe since I still have like 7 minutes, I will briefly talk about the proof for the first and the second part of this proposition. So as I mentioned before, when M is 1 and 2, then the fibers of the quadric fibration will have co-rank at most 1. So in this case, the first map from the Hilbert scheme to the double cover will be a P1 fibration. And then this lines intersecting the smooth section will be isomorphic to your double cover, and then this will give you a section to the P1 fibration. So this tells you that the Hilbert scheme is actually a P1 bundle over CM. So there exists a rank 2 vector bundle on CM. And then from computation, you can know that when you take the endomorphism of the vector bundle and then push forward along the double cover, and then you will recover the even Clifford algebra. And then tautologically, this tells you that you have like equivalence of this non-trivial component with this DBCM equipped with endomorphism. So that's how we would get, the second part here. So explicitly, when M is 1, you get the double cover is actually the smooth conic, so it's just the P1. And then in this case, it can be computed. The rank 2 vector bundle is O plus O minus 1. So the Hilbert scheme is just the Hertzsprung surface F minus 1 over P1. And then when M is 2, you will have the double cover is the chain of 2 P1. And then the rank 2 vector bundle is O plus another line bundle, where when you restrict this line bundle to the 2 components of P1, you have the degree is -1 and 0. So this kind of concludes this, the first 2 cases. So the non-trivial case would be when M is 3, because in this case, your fibration has a worse fiber. The fiber has corank 2. So then this is the quadric surface. And then when you consider lines in it, then either the line is contained in one of the P2, then it will also corresponds to P2, or contained in another P2, and then it corresponds to the other P2, and then they will intersect at a point corresponding to this line. So you will have something 2-dimensional, and then so the Hilbert scheme will actually be terrible. But if you kind of restrict, as I mentioned before, then the picture you would have is your L3 is a train of 3 P1, where the map from L3 to the double cover is contracting the second P1 to the point. And then it will map to the point where the fiber has corank 2. So then in this case, to study this non-trivial component, we can still lift this to the double cover, because we can always find a sheaf of algebra on the double cover where the push forward is your B0. And then you also have this equivalence. But then the problem here is this sheaf of algebra is not as Maya, because you have a word singularity. So if you restrict the sheaf to the locus away from that point, then you will have this is rank 4 in Azumaya. But if you restrict this sheaf to this point, then you have this is 6-dimensional. So it won't be the endomorphism of some vector bundle. And then, so this construction is kind of trying to resolve this problem where you extend the point to a P1. So then it is possible to find a rank 2 vector bundle on this new space such that the push forward will give you an equivalence. And this is how you understand this non-trivial component in this case. I think I will probably stop now. And thank you for listening.
Okay, yeah, thank you very much. Let's thank Fei for the talk virtually. So any questions?
Hi, can I ask a question?
Oh, yes.
Yeah, I was wondering, maybe just a stupid question. I was wondering whether you have studied this semiorthogonal decomposition for this X22?
No, not yet.
It's Nodal X20. Is there any result on this X22? Maybe I should ask this Pavic and Shinder professor.
Yeah.
So they're not classified, I guess. Even the nodal V22s are not all classified. I think.
Okay.
So for V5, there's only 3, and for V22, it's a lot.
Okay. Okay, maybe another question. I was wondering whether, I mean, if for example, for this Y5, this in your case, this nodal Y5, whether this component will also contain some birational information about this variety. For example, maybe whether this Fano surface of lines can be described using this component, as in the classical smooth case. I mean,
I'm not sure about using the semi-orthogonal decomposition to describe the Fano surface of lines. Let's see, let's come back here. So I should say I can't say anything about that from this SOD, but when I was trying to construct this rational map, yeah, okay. I think
never mind. Yeah,
like,
because I think, for example, if you take the ideal shift of line, it is still in this component, right? By this just computed the ideal shift line. I mean, it is still in this orthogonal complement of this O and O1, right?
probably.
So I'm just guessing from this smooth case, this Kuznetsov component. I mean, the ideal shift line is in this Kuznetsov component. So here is kind of analog of that constructions. So I was wondering whether, because in that case, the Fano surface of line can be realized as some this stability. I mean, this moduli space of this quiver. I mean, the stable representation of the quiver. In that case, I was wondering whether the similar story can happen here. Yeah, I'm just curious. So,
okay. I haven't thought about this, so I don't know the answer, but I see what you're trying to do here.
thank you.
Is the Fano surface of line just P2 in this case or something, right? And then when you degenerate, you get multiple components.
Mm-hmm.
Probably it's good to describe those components, but they're all a bit like P2.
Actually, for XM, you just get, I mean, if M is not 3, then each singular point gives you a component isomorphic to P2, and the main component becomes P2 blown up in M points. So, I mean, the description of the Hilbert scheme of lines is quite straightforward.
Cool, thanks, Sasha. Any more questions to Fei? So I guess I have a question. So what would be the general statement if you have a quadric bundle over P1, right? So can one make some kind of general statement about, I I mean, yeah, so how would one generalize this?
Generalize.
Let's say you have a singular threefold, which is a quadric bundle over P1. And I guess your main thing was describing the modulus of a Clifford algebra in terms of a certain singular curve.
Yeah, actually, this is something I'm working on right now. I think what you're saying is you're trying to, let's see, understand this it's not working. The non-trivial component dBp1 B0 when your quadric fibration has like worse singularities. My expectation is that if your surface vibration, the quadric surface vibration has a smooth section, then this non-trivial component is probably equivalent to the derived category of a singular curve, where this curve is just the double cover, adding some P1s where like over the worst singularities, you're adding P1s, just like the case I discussed here. Here you only have one bad point. You're just adding one P1. But you have more, so I guess you would add more. But that's just my expectation.
Thanks. Is this geometry equivalent to blowing up the section and realizing it as a P2 bundle, right? So if you have a quadric with a point, you can transform it to a P2. If you have a small section, you can transform it to a P2 bundle with a roof, right? Blow up, blow down. And is what you're doing more or less this?
I don't think I quite follow the construction you're trying to do. I think for me, I'm more like using consider like lines intersecting the section. This is kind of one suggestion to make it work.
But it's exactly, you know, if you have a quadric with a point, you blow up the point and contract lines through that point, right? The two lines in the smooth case. And it makes you a P2, right? This link between P2 and the quadric. You blow up a point on the quadric and contract two lines. And you do this in families, right? So your lines through the section is exactly what you contract onto the other side, which, yeah, we can talk about this later. Yeah, cool. Any more questions to Fei? Okay, so I guess, yeah, thanks again. We finish now and we can have an informal chat and gather town for people who would like to.